Welcome everyone to a session on Unix programming. In this session, we will start module 4, and the first chapter in module 4 is process control. Obviously, we had process control in module 3, right? So some of the topics which were not covered in module 3 is continued in a new module, that is module 4. Okay, so we will look into the topics belonging to process control in this particular session. The first topic is changing user IDs and group IDs. So before looking into the syntax of the function that can perform this changing of user ID and group ID, we have to understand why it is necessary to perform the changes, right? See, a process, its ability to read or write a particular file depends entirely on the user ID and the group ID to which it belongs to. And when a program needs additional privileges or need to access resources that they currently aren't allowed to access, then it is necessary to change their user or group ID to an ID that has appropriate privilege or access, right? So normally when I talk about this ID that has appropriate privileges, I am talking about the root user privileges, right? So I need to change the ID to the root user ID. Okay, and similarly, when our program need to lower their privileges, sometimes it is necessary even to lower the privileges or prevent access to certain resources. They can do this by changing their user ID or group ID to an ID without the privilege or ability to access the resource. Okay, so this is the vice versa of the previous case, where super user need to lower or the process belonging to super user need to lower its privileges to prevent access to a certain resources. Okay, and before looking into the function, we will see the various types of user IDs. Okay, basically there are three different UIDs for a process. See, every user in Unix like operating system, including Linux, is identified by a different integer number, and this unique number is called as user ID, right? And there are three types of UID defined for processes, okay, which can be dynamically changed as per the privilege of the task, and these three are the real user ID, the effective user ID, and the saved user ID. So what is the real user ID? So the real user ID, it is the account of the owner of this process, the one who has created this process, okay, and it defines which files that this process has access to. So this is about real user ID. And what is effective user ID? See, the effective user ID is normally as same as the real user ID, but sometimes it is changed to enable a non-privileged user to access files that can only be accessed by the root user, okay, or the root processes. Finally, the last one, saved set user ID. So it is used when a process is running with elevated privileges. Generally, it is root processes, okay, and needs to do some underprivileged work, okay. So this can be achieved by temporarily switching to a non-privileged account. So while performing this underprivileged work, the effective user ID, so this one is changed to some lower privilege value, and the EUID, that is nothing but the effective user ID, is changed to saved set user ID. So this will be saved to saved set user ID, SUID, so that it can be used for switching back to the privileged account when the task is completed. Which task is completed? The task of with the lower privileges, right? So when that task is done, you can reassign it by swapping the value that is present in the saved set user ID. Okay, so these are the three user IDs associated with every process belonging to the system. Okay, real user ID, effective user ID, and saved set user ID. Okay. Now we will see how the changes of user ID and group IDs can be done. We can set the real user ID and effective user ID with the set UID function. Okay. So this set UID function is used to deal with UIDs, that is a user ID. Okay. So it is possible to set the real and effective user ID using this function. Similarly, the set GID function is used to set the real group ID and effective group ID of the process. Okay. And what value does this return, these two functions return? It returns the same value, that is it returns 0 if the function is successful, and -1, the value of -1 when the error has occurred. Okay. And there are certain rules for who can change the IDs. Okay. So for time being I am referring only to user ID, and the same is applicable to group ID. Okay. Okay, so let us see the three rules. So if the process has super user privileges, then the set UID function sets the real user ID, effective user ID, and saved set user ID to UID. Okay, so only if the process has super user privileges, the set UID function sets all these three user IDs, UIDs to UID. Okay, that is real user ID, effective user ID, and saved set user ID to UID. Okay. And the same is applicable with group IDs. It can, using the set GID function, it will be able to set the real group ID, effective group ID, and saved set group ID to GID. Okay. So second rule is, if the process does not have super user privileges, but the UID equals either to the real user ID or the saved set user ID, then set UID sets only the effective user ID to UID. Okay, and the real user ID and the saved set user ID are not changed. And the same is applicable with group ID. If the process does not have the super user privileges, but its GID is equal to either the real group ID or saved set group ID, then get UID sets only the effective group ID to GID. The real group ID and the saved set group ID are not changed. And finally, if neither of these two conditions is true, then error number is set to this error, which is error with respect to permission, and -1 is returned. Okay, so these are the three rules what we have to remember while performing the changes, or with which I can perform the changes of user ID and group IDs. Now let us see the variations of set UID and set GID function. The first one is set REUID and set REGID function. So this is used for swapping the real user ID and the effective user ID of the process. And yeah, this is the syntax, and it returns 0 if successful and -1 on error. Okay, and we can supply the value of -1 for any argument to indicate that the corresponding ID should remain unchanged. So if I want to keep it unchanged, then I'll supply the value -1. And the rule is simple. An unprivileged user can always swap between the real user ID and effective user ID by using this function. Okay. Yeah. The next one is set EUID and set EGID function. Okay. Very similar to that of set UID function, but this works only for effective user ID and effective group ID. An unprivileged user can set its effective user ID to either its real user ID or its saved set user ID. For the privileged user, only the effective user ID is set to the UID. So this is how it is different from set UID function. Okay. And to summarize these three functions and its operations is depicted in this particular diagram. Okay, so as you can see, the set UID function, first one, the let me point it to it. Okay, the set UID function for a super user, all real user ID, effective user ID, and saved set user ID is set to UID. So this is what we have seen, right? And set REUID. So that, as previously said, for an underprivileged user, it is used to swap the value of. So for an underprivileged user, it is used to swap the value of real user ID to effective user ID and vice versa, right? And set EUID. So this, as said, is applicable only for effective user ID. So this is the only change with respect to EUID for a super user. It will set only the effective user ID to UID. Okay. So this diagram summarizes the functions what we have seen previously, right? So this is about changing the user ID and group IDs using the function, and we have concentrated, or in my explanation I focused only on UID, but the same is applicable for group ID also. Okay, so whatever that is applicable here for the group user ID is applicable for group ID. Okay, yes. The next topic is interpreter files. So what is an interpreter file? It is nothing but a normal text file, but a text file that begins with the symbol, okay, or this particular line, okay, shebang. We call this as shebang, right? We have already seen this while writing shell script. Okay, so what does this say? This symbol indicates that the next topic is interpreter files. So what is an interpreter file? So these are the files, these are nothing but text files that begin with the line of the form hash, using this symbol hash exclamation symbol, followed by a path and followed by optional arguments. Okay, and we have already seen such kind of interpreter files. Your shell script whatever we have written is an example for interpreter files. Okay, so what does this what will be the first line of a interpreter file? It will have this symbol which is called as shebang. And what does this represent? This represent that the entire file consists of commands which need to be fed to an interpreter that is specified in the path. Okay, so the program, the shell script itself is not an interpreter, it's a interpreter file, and the interpreter is mentioned in the path followed by the shebang. Okay, So we will take some example. See, so this is an example for an interpreter file, right? So this shebang followed by /bin/sh. What does this say? This says the following commands in my shell script need to be executed by the shell which is specified in this particular path. Okay, and by default, um, when I refer to sh in Unix, it refers to Bourne shell. But see, it is also possible for us to have different shells of our choice, isn't it? So if I want to execute the commands in the interpreter files in the shell script by using C shell, then I have to specify the path to the C shell. This is the path in my first line, right? In the first line. And this is an example for a Perl script. Okay, the Perl script begins with this, right? And also if you see Python programming, you can find a path to the Python interpreter in the first line by making use or prefixing it with shebang symbol, right? We call this as shebang, hash followed by exclamation symbol. Okay, example is this is a program. Okay, so this first line is of the form represented here, right? So I can say that I can very clearly say that this is an interpreter file and this is the interpreter. This is the path to the interpreter. And what will happen in this when I execute this program? Each of these commands, okay, each of these commands will be executed one by one by the interpreter, which is a shell that is specified here. Okay, so first one, see, the second line is also starting with hash, right? So but this is a comment line. We know how we write a comment in shell script, right? So this need to be very clearly differentiated. So this is a comment line. No, nothing will be executed here. This is not a command. The third line, the third line in the interpreter file is an echo command. So hello world will be executed by the shell that is specified here, right? And followed by date. Okay, once I am done with the echo command, then date will be executed followed by ls command. Okay, so these three commands will be executed in order by the interpreter that is specified here. So this is a classic example, a simple example for interpreter file. Now we'll see the system function. What is the use of the system function? See, sometimes it is convenient to execute command strings from within a program, right? And the system function allows me to write or allows me to execute Unix commands inside a C or C++ program. Okay, and yeah, let us see the syntax of Unix function. So this is the syntax. Okay, it takes argument command string. So what is passed as an argument to system? The commands that need to be executed in the program need to be passed as an argument to system. Okay, and what if the command string is a null pointer? So in that case, system returns a non-zero value only if the command processor is available, or in other words, it will return a non-zero value only if the system function is supported by the operating system. And the Unix system, obviously the Unix system will support this system function. What about other operating system like Windows? So in Windows, if I try to execute system, then it will throw an error, right? Okay. Okay. Now, because system is implemented by calling fork, exec and wait PID function, there are three types of possible return values. So let us see each one of these. First one is, see, if the fork fails or the wait PID returns an error other than interrupt error, the system will return -1 value with error number set to indicate the error. Okay, so this is the case when fork itself fails or wait PID returns an error other than interrupt error. Okay, so the other case is if the exec fails. So if the exec function system call fails, which implies that the shell cannot be executed, right? Then the return value is as if the shell had executed exit. So this is as same as the value 127, where a shell, it is as equivalent as a shell executing an exit command with the value 127. Okay, and lastly, if all the three functions fork, exec and wait PID succeeds, then the return value from the system is the termination status of the shell. Okay, so this will be nothing but the exit status of the shell after executing the commands. Okay, so this is in case of all these three function is system calls are succeeded. Okay, in other words, if the command is successfully executed, then the exit status of the shell will be returned as a return value for this system function. Okay, now let us see a few programs, or let us see some example. See here, system. What did I pass here? Here we pass this command line, right? So this, in this case, first example, date is executed and the output of date is saved in a file. Okay, and this is passed as an argument to system. In the second example, ls minus l, where I want to list the files and directories present in the current working directory. So this is passed to the system function. Here I perform cat function, or display the content of foo, file name called as foo, and this is passed again as an argument to system. And finally, multiple commands are executed. Here move command and this thing calendar, right? So this is two commands, more than one commands are executed by passing it in a single command line to the system function, and it is delimited by using a semicolon. So this separates the two commands, right? So this is one command, this is the followed by another. So this is how these are some of the example of system function. Now let us see some examples, program examples of making use of this system function. Okay, yeah, system, as previously said, is used to execute the commands that are passed as an argument to it, right, in the form of command string. Okay, now we will let us see the example, one example program with respect to fork, exec and wait system call. Okay, now see, first thing here, so let me not elaborate each and every line of the program. So we will look into the major part. If the command string, if it is equal to null, so if nothing is passed, or if no command is passed to system, then the return value is a non-negative number 1. So why I have to return 1? Because see, this there is always a command processor with the Unix, right? So if the system is supported by the operating system, and if the command has to be null, then I have to return the value 1. Okay, now then using the fork system call, a child process is created. Okay, so the two copy of this process will be created. One goes to the parent and one goes to the child, as we all know how the fork system call works. Then yeah, so this is only to check whether the child, whether the return value of fork, if it is less than 0, then I'll return the value of the status as -1. Okay, so this is a fork error, right? Okay, if the PID value, if it is equal to 0, now we are talking about the child process, right? So this is about the child process. Child will always receive the PID equal to 0 on successful creation, right? And the parent, what it will receive, it will receive the PID of the child, right? So that is another copy. So that comes here in the else part. Let me not explain that. Okay, so if the PID is equal to 0, what we will do, we will exec, we will call the exec function, and path name to the shell, right? The shell is executed. I will call the shell, and what is passed as an argument to shell, so that is nothing but the command string. So So these command strings, the value of the command strings, which are nothing but the Unix commands, will be sent to this, right? Will be sent to the shell, right, which is specified here. Path to the shell is specified here using the exec system call, right? So each of these commands will be executed one by one, right? And um, if if it is not possible to execute this exec system for call, then exit function with the 127 will be, or 127 will be returned. So this represent execl error, right, as previously said. Okay, so this is a demonstration of how we make use of the system program, or system function in terms of fork, exec, and wait to execute the commands that is specified here, right? Okay, so what do we do? So first check whether the command string is null. If it is null, then we return one value, -1. We return a positive value 1, right? Then we fork a child, and inside the, if the child is successful, what do? We call the exec function, and we specify the path of shell. So we override this child process with the image of the shell process, right? And what is passed as an argument to this shell? Whatever that we wanted to be executed, all the commands that we wanted to be executed by the system is passed as an argument to exec, right? So this is the demonstration of this program. Okay, let us take two more example. Okay, so this is another program where we do not make use of fork, exec, and wait system call. So this is another demonstration of the working of system. Okay, so here we have defined one variable status. Okay, and see, the first, here we make use of the system call to execute which command? Date command, right? And we check whether this is executed. See, if the return value, if the status value, if it is less than 0, then obviously this cannot be executed, so we will display an error message, right? But if it is not true, if it is not less than 0, if date is successfully executed, then we will display the exit status of the will print the status value, that is nothing but the exit status of this particular command date, right? Okay, let us see the output later. And see, in this case it is specifically mentioned, or intentionally some non-existing command is passed to system, right? The command name is no such command. So this is the command that is passed to system. And again we do the same thing. What do? We print the exit status of a system, that is this value, after executing, or after trying to execute this commands using the system function. Okay, let us see the value later. Okay, the last one here. Okay, the who function is passed as an argument to system, and after that exit 44, exit with the value 44 is passed. So what does this will do? This will execute who command, and it will return, or it will exit with the value 44, right? So here it is specifically mentioned that the exit status value should be 44, right? So these are the three cases here. One is a valid command date, we shall see the exit status of this. An invalid command, that is passed to system, and a who command, which is a valid command, and specifically the exit value is mentioned here, right? Okay, so this will be the output. Okay, so if I compile and execute this, then date will be executed. So this is the output of date, and it's a normal termination. Exit status is 0. So why the exit status is 0? The exit status is 0 because date is a valid command and it is successfully executed, right? So the value is 0. And what for no such command, this one? So the output what I get is command not found, because it's an invalid command, right? And the exit status is 127. So why it is 127? Because um, this command was failed to be executed, right? So it doesn't exist, right? So we exit using this value 127, which is nothing but the exit status of the shell if it fails to or if the execl function fails, right? Okay. And finally the output of who command. Okay, output of who command, and the exit status value as previously said is 44. So this is for this one, this exit. I am talking about this exit, right? Who and exit. Okay, we'll see one more example. So this is nothing but another program where we pass command in the command line argument. Okay, the command that need to be executed is passed in the command line argument of while executing this program. Okay. Okay. So again, status. If the argument count is less than 2, then we display an error message, command line argument required, right? Because along with the executive this dot slash a dot out, I need to specify the command that need to be executed, for example ls, right? So if I don't specify both of these, then obviously one is missing. Obviously this command is missing, which will be displayed here, right? Then command argument 1, in this case if it is ls, that is passed as an argument to system, then the exit status of this command will be displayed. Okay, exit status of this command will be displayed. So this is about yeah, obviously if the ls is if it is a valid command, yes it is, right? The exit status what I get is 0, isn't it? So this is about the system function, and we have demonstrated the system function using these 3 programs, right? The first one by using the fork exec and wait. The second one we have demonstrated 3 commands, right? The date, then a non-existing command called as a no such command, and followed by who command with the exit status 44, and finally this one where a program reads a command from the command line argument, okay, and executes this command by passing it to system, and the exit status of that system call is displayed. Okay, so this is about system. So we'll look into the more concept on this chapter in the next coming video. I'll see you all in the next one.